I'm Nick Bray. I work at Google on Chrome. And lately I've been working on a new technology called WebAssembly. I've been working on this with a handful of coworkers and other software engineers at other companies. WebAssembly is designed to run native code on the web. Run it quickly, run it efficiently, run it safely, run it performantly. And by themselves, we've seen this all before. When I say native code, I mean C, C++, or anything that compiles down to a machine architecture. And native code naturally runs fast, right? Well, getting this all together, getting it to run on the web, is we've had pieces of the puzzle for a long time, but WebAssembly, I believe, is going to be the first thing that puts all the pieces together. So the two reasons I'm very interested in WebAssembly are everyone's talking about it. Or I should say the major browser vendors are talking together about it. Now, this is a far way away from actually being a standard. This is a far way away from everyone committing to it. But the fact that we're talking is a very good sign for what's coming. The other thing that I'm very excited about is that it has shared memory multi-threading. Now, there's a lot of front-end developers in here, and front-end developers, please raise the hand so I know who I'm talking to. And then people with experience with native code. Okay, so it looks like we have a bit of a split with a little bias towards the native code. So I will explain shared memory multi-threading in a bit, especially for the front-end developers, but this is very, very important to get native code to work and work very well. So we've been down this road before. Is native code on the web, we've been trying at it for, I don't know, about 5 years now. And it's never quite worked, but there have been some things which have been really impressive, in my view. One of the things that's occurring nowadays is game engines on the web, is Unity on Unreal. They're taking their game engine, which is currently targeted at desktops on mobile, and then they're adding components so they can run on the web. And this shows a sort of cross-platform strategy. You're looking for all the distribution channels you can for your content, and the web is just another one. Currently, it's a little tough, because the web is weird, as we'll get into in a moment. But if it was less weird, if you could just target everything at once, more opportunities for revenue, more opportunities for delivery. Imagine if you could just send a link to someone to the game. Your friend clicks on the link, then they're in the game immediately. No install, they're right next to you. Just works. There's been some interesting experiments with running different languages on the web. Right now, you can use any language you want on the web as long as it's JavaScript. And there's a website called Replit, which has been using technology to compile native code to JavaScript to run things like Python on a web page, run things like C# on a web page. Even crazier people are emulating entire operating systems. There's a website called DOSBox where you can run all your favorite old games if you're that old. JS Linux is someone run an entire Linux machine and translate it to Java in a web page, so you can do Linux in a web page. One of my coworkers set up an entire development environment inside a native client module, so you can run GCC inside of a web page. Crazy stuff, impressive stuff. And people have experimented with PDF viewing, is that you could actually compile a PDF viewer and run it inside a web page. Traditionally, PDF viewers are part of the web browser, but they actually made it a web app. And similar with media decoding, there's some places that people have taken media decoders, audio decoders, and run them inside the web page. Again, traditionally, these things are part of the web browsers. If you want to decode video, you say, well, my program isn't going to do that, so I'm going to delegate to the web browser. And there's a lot of reasons for this, that the web browser just isn't fast enough in a lot of cases, or I should say web apps are not fast enough. But I mean, they are fast enough in the throughput sense, but sometimes they just aren't reliable enough. You know, if you're trying to decode audio, you have to do it exactly when the audio is needed, or else there's gaps, there's pops. So performance is more than throughput, it's also reliability of performance. So right now, all of these things are very interesting, and they work in many cases and almost work in some cases, but they are the product of very dedicated people. And if we lower the bar to entry, things like this will become much more common, much more pervasive. So the problem with the web is that it had its own evolutionary history. It responded to a different set of forces than the native platform did and ended up in a different place with an entirely different set of properties. Now, different isn't bad, but when we're asking how can we do multi-platform development, how can we take legacy code and move it to the web, it becomes much harder because it's different. So one big property of the web which is different is this asynchronous. Is that if you ever want to ask the system for something, say load a file, you say, hey, I want to load a file. The system says, that's great, give me a callback. So you give it a call back and it says, okay, I'll get back to you later. Now, if you're still executing, you'll never get the response. In fact, the only way you can get a response when you're running JavaScript is that you stop execution. You unwind your entire call stack, go back to the event loop. The event loop may do a few things in the meantime. You have no control over what it's doing. And then eventually it'll call you back and say, oh, yeah, here's the file you requested across the network. Native code, on the other hand, likes synchronous interfaces. This is a legacy of how the operating systems first were, is you go to the operating system and say, hey, I want a file, and it says, stop right there for a moment. Goes, gets the file, then says, here's the file, resume. So the interesting thing here is that you don't unwind the call stack. You have the entire function call chain, you get the file, and then you can resume execution immediately from where you're at. So if you're trying to translate a synchronous program into an asynchronous program, this ends up being a lot of work because you have to cut the entire call stack. You have to change things. So every time you had what used to be a synchronous operation, it becomes an asynchronous operation that turns into a callback. Another aspect that makes porting to the web fairly hard is that there are no threads with shared state. So if you're familiar with the web platform, there are web workers, which are technically threads. But they have their entire own JavaScript context. They have their own set of objects. And you can never have an object that is simultaneously modifiable with two threads. Where when you have something like the native platform, when you have threads, you can freely pass data to them. And you can actually access data at the same time, which is usually a bad idea unless you're very, very careful. Even the people I work with who are expert at threads, when you ask them, how does this work, they're like, let me think about that for a moment. And that is called wisdom, as people realize they are not as smart as they think they are, and threads are tricky. So when you're porting native programs, you want threads because they, despite the fact you're juggling hand grenades, is they give you things that you need. They give you performance. They give you reliable performance. They are essentially the primitives that the CPU uses. So you can't really get any more efficient than that. You can't get any more reliable than that in a lot of ways. You can debate whether you actually want threads as a programming model. They are dangerous, but they are very, very useful. So having a platform that provides them to you and lets you build things on top of them, lets you build better abstractions on top of it, that's pretty important. Another weird thing about the web is inconsistent performance. JavaScript was designed to be easy to use. And it's only over time that we've been able to make it run faster and faster. And this is in part due to the heroic efforts of the people implementing JavaScript, is they've gotten cleverer and cleverer. And the JavaScript engine has gotten more complex and more complex. So when you ask, why does my JavaScript application perform the way it does, the answer is not very clear. So there's all sorts of just-in-time compilers, which start at the beginning saying, well, I know nothing about your program other than its text. Then it starts executing it for a while, then says, oh, wait, this is a number. I can do a little better. So then it runs faster. Then it says, oh, I know the type of this. Then it can run better. Then it says, oh, whoops, I got new information that says this could be a number or string. Oof, I don't know what I'm doing, so let's run slower. So you can actually have, through the lifetime of your program, that run faster, then run slower, then run faster. And it's because of the heuristics and the tuning and the magic, which on average makes the web go better, but for your specific application, it may result in bizarre behavior that you can't explain. Another thing is garbage collection. JavaScript provides the abstraction that you don't have to deal with memory. So if you ever done C or C++, manually saying, I'm done with this object, it's very error prone. If you do C++ for long enough, you sort of get in the habits, you know how to do it, but ultimately when you get it wrong, that becomes the worst bug in the world to deal with. So garbage collection fixes all this by saying the system will figure it out for you. But the cost of this is that occasionally the system has to come in, stop the world, and say, let me clean up after you, then resume the world. And this is GC pauses, is when you have a JavaScript application or any application with any application with memory management, is if you're trying to do rendering 60 frames a second or rendering audio, in the worst case, you could be interrupted and there could be a bit of a hiccup. So altogether, porting code to the web is currently painful, no matter how you do it. And the question is, how can we do better? So you might think that maybe the web just isn't worth it. There's all these things that makes porting native code to the web hard, so let's just not do this. Let's the web set on its own strengths. But it has a lot of interesting strengths for other developers. It's open. So you want to ship an app, all you have to do is get a cloud server somewhere. Load it on there, boom, you're an app publisher. There's also multiple vendors who have different browsers. You never have to worry about vendor lock-in for any web standards because there's multiple implementations of it. It's secure. Now, there should be an asterisk next to this, is technically every platform is secure. But they have a different definition of security. And the web has a fairly unique definition of security that it's as safe as a document. So the history of the web started with viewing HTML documents, and the security model keeps going from that. So when someone hands a document, you don't have to worry about it picking your pocket. You know, it's not going to harm you in any ways. Your eyes aren't going to explode. A document is safe. There's nothing anyone can do to damage you by giving you a document. Other platforms, they have a different approach to this, and this has caused legacy problems. Like operating systems assume any program is operating on your behalf. So therefore, if it wants to take your tax return and upload it to some strange server in some foreign country, that's a perfectly fine thing to do because that's you doing it, which isn't true for many apps which are loaded across the network. Another thing is it's portable. Again, this is an attribute that deserves an asterisk next to it. It is portable in the sense that anywhere there's a web browser, web content can run. And the same program should run the same anywhere. So if you're used to native code, you spend a lot of time porting it. And native code is portable in the sense that you can make it run on any machine fast, but there may be behavior differences between it. So things are a little different between platforms. So there's two distinct different versions of portability, and the web's version of portability is that consistent behavior no matter what the operating system, no matter what the CPU. Another nice property which sort of springs from the security and portability is ephemerality. You don't have to install it. You just point your web browser at the app, you're up and running instantly. And as it turns out, when you have to ask users, oh, can I have permission to do bad things to you, but honestly, I will not? This sort of reduces the user buy-in. It adds friction. It makes it harder to convince them to use your app. Similarly, ephemerality allows the idea of evergreen apps, is that every time someone goes to your web server, they get the newest version. You have to worry less about tech support for someone who's using the application that's 2 years old. And then you're scratching your head figuring out why did they have such a weird thing going on. So wouldn't it be nice if we could get all of these properties of the web and all of the good properties of native in one bundle? That's kind of the question that's motivating WebAssembly. And I should say at this point, I'm going to refer to it at WASM at some points, WASM, and that's just habit because we've been talking about it internally so long and we have jargon. So to understand how we got here, we should briefly look at the history. And as I was saying, that in the first, there's hypertext markup language, which was just a document. And then a few years later, people figured out interactive documents are cooler than just documents. So this is where JavaScript came from, is you can click on it, and that's an event, and you respond to the event, and then you return to the event loop. But people wanted more. So they immediately saying, hey, we have this nice document distribution platform. So what if we could have other kinds of documents, like PDF documents, or vector graphics, or we could embed Word documents? So there's this profusion of plug-in technologies where people said, hey, we want to do more in the web browser, but instead of doing it inside the web browser, let's just bolt this chunk of code into the web browser. And the legacy is still with us today, 20 years, we're finally dealing with this. But the problem with this is there's severe security problems. Is that because you weren't inside the web browser, because you weren't thinking about how to behave as web content, because you were your entire own stack, you could have just different rules for what was secure. And it was sort of like when you had the two parents and you're like, hey, can I do this? No. Hey, can I do this? Okay. And once you're in that situation, it's very hard to be secure. And there's surface area, complexity issues. So in some ways, we had the best of intentions in this era, but we didn't quite understand all the nice properties of the web I said earlier. Around 2008, there is a renewed interest in JavaScript performance. Chrome came out, Mozilla started really pushing their JIT, and suddenly JavaScript became fast. It became practical to think about building large-scale applications in JavaScript. There's an exponential takeoff, and everyone was like, magic JavaScript elves are making things faster all the time. But I actually know those JavaScript elves, and as it turns out, this is very, very hard. And the amount of complexity involved is huge. And so this exponential takeoff we saw around the 2008 era is not sustainable. Is there's a certain ceiling where we're going to slow down progress and slow down progress. And the question is, how do we keep going? How do we keep getting more performance? And WebAssembly kind of answers that by saying we do it by being simpler, is we make the browser's life easier in order to make it run fast. A project that I worked on was native client. Is Google said, hey, what we're going to do is we're going to take a native programming environment, figure out how to make it safe by making sure it can only talk to the browser, not talk to the operating system. And there you got native code on the web. Unfortunately, they did not get buy-in from other browser vendors. Is in my point of view, from my point of view, it's the right technical solution, but it never got the multi-party buy-in, the cross-browser solution. And this always made it a very hard sell for web developers. Is, you got Chrome, great, but what about the other 50% or so? That's a very hard thing to overcome. Web developers want to run everywhere. They want it to be a web technology. They want it to be fully open and fully portable. So around 2010, Mscripton came on the scene. And at first blush, this is a truly horrifying idea, is that you take native code and compile it into JavaScript. Now, this was just after JavaScript started becoming fast, so people were still in the mindset of JavaScript, isn't that slow? But due to some very careful engineering decisions, it was able to run shockingly fast. And it actually just worked a lot of the time. The big limitation of Mscripton is that because it was being compiled to JavaScript, it couldn't do threads effectively. It had to use JavaScript's concurrency model, is you had to have the event loop, you had to be asynchronous, you could not block. So there was always a bit of porting friction where you had to rework your model, your application's model to work inside JavaScript's application model. So this brings us to WebAssembly, is what if we could have the nice pervasiveness of Mscripton, but at the same time have shared memory concurrency? So this is kind of a summary of that somewhat long-winded history thing, is if you look at the top, that's the plugin era. And the obvious problems there are security. And another thing that came along is because there's security, there's sort of grudging acceptance of things like NPAPI. So when the mobile browsers came out, they said, that's technically not part of the standard web, so we're not going to support that. So Apple's decision not to support Flash, for instance, that was a real big impetus to re-examine these technologies. And because of that, they aren't really cross-browser anymore. Even though one version of Chrome supports Flash, the mobile version does not. Then if you look at the right corner, or the right column, this is the one that particularly interests me, is there's really no platform right now that both runs in every browser and supports shared memory multi-threading. And that's one of the big things making it easy to run native apps on the web. So WebAssembly, potentially. So enough history. How does WebAssembly actually work? And the answer in some ways is very simple and very boring, is that you're used to a normal web app, and that web app takes in an HTML page, takes in JavaScript sources, takes in data files like images, CSS, things along those lines. And the WebAssembly, when the browser supports WebAssembly, there's just going to be a binary. It's going to be a binary produced by a C compiler from C source files. And then you just load into the browser, much like you would JavaScript, has its own VM, turns into a bunch of functions, turns into a bunch of code inside the browser. Now, I'm lying a little bit. In fact, as an implementation issue, a lot of the people who are planning on implementing this are planning to fuse the JavaScript and the WebAssembly bits. So when you actually have a WebAssembly file, what's going on is you're taking it and you're shoving it into your JavaScript engine just at a much lower level. Is the WebAssembly file, you know more about it from the beginning, so you can skip all of the dynamic and adaptive compilation things where you're trying to figure out, is this an integer or is this a string? You know from the beginning. But this is an implementation detail. From the user's point of view, you don't know, you don't care. What's actually inside this binary file? It's rather hard to make slides about binary. So here's an image to illustrate it. So if you have an example, you're calling the function foo, and you have one argument, which is a plus 7, another which is b. Both a and b are locals. If this was JavaScript, you'd initially say, well, I know nothing about this. I don't exactly know what function I'm calling. I don't know if a is an integer. I don't know if it's a string. So this addition operation, it could do a lot of things. It could concatenate, it could add, et cetera, et cetera. But in the WebAssembly version is you have a tree of operations, and each of those operations you can exactly infer what it's going to do. So when you have an addition operation, it says this is the type of it. It's an int32 operation. So the inputs are both going to be 32-bit integers. The output is going to be a 32-bit integer. And this allows you to have good performance from the beginning. The binary format itself is important because it allows us to be smaller. So if you just take a JavaScript application, compiled to WASM.js, and then transcode it to binary, one of the software engineers at Mozilla did this experiment and found that they could reduce the file to about a third the original size. But this is before compression. If you actually compress it, there's sort of an entropy argument in play that it's still the same program, so it's still going to be about the same size. But nonetheless, they were able to shave off about a quarter of the size. Now, size is very important, especially on the web, because it's data. It's how much do you have to download. And this also affects how fast you start up. It also affects how often can you update your app and things along those lines. So the smaller you can get it, it pays dividends in all sorts of other ways. And I should say at this point, I've harped on performance. And again, performance is one of these things that is more than just how fast you run. It's mobile battery. It is the difference between 4 frames a second, nice hack, and 40 frames a second, oh, this could actually work. So performance is a feature. It isn't just the same application running faster. Another interesting thing about the binary format is that it's about 23 times faster to parse than text. So because it's binary, because it's not designed to be human readable or human writable, you can lay it out in such a way that the machine doesn't have to think too hard when it sucks it in. And parsing the JavaScript is actually a fairly large component of startup. And JavaScript engines do things like overlap it with the download to try to amortize it, but it's fundamentally expensive. So what's actually going on under the hood? I've waved my hands about binary encoding and things like that, but what does it actually do? And when I first did this slide, I was like, wow, this is kind of boring. Is that WASM, you get a big chunk of memory, a big bunch of bytes. And you take bytes out of it, you do operations on them, and you shove bytes back into it. There are no objects. There are no strings. This does not look like anything you expect to be a programming language, especially if you're coming from the JavaScript world. But after thinking about it for a while, I realized the important thing here is this is not a programming language. What this is it is a portable machine architecture. It's kind of equivalent to a CPU in a sense. A CPU has a bunch of memory. It has can do arithmetic operations. It can move things in and out of memory. You build programming languages on top of this. So you take something like C, it gets compiled in terms of this. You take something like C++, it gets compiled in terms of this. So for example, if you have a C program with its nice manual memory management, whenever you create a new structure, a new object, it boils down to say, hey, I want to allocate enough bytes to hold the data structure in. So I want to allocate 100 bytes, and then it does some bookkeeping. Your program itself says, I know I have this big chunk of memory, and based on bookkeeping, I know this area is free, so here, have the address of these 100 bytes. And then you can load numbers in and out of that specific region, and that corresponds to fields on your data structures, for example. Another thing going on here is that you have a limited amount of memory. Is hopefully large, but still limited, because this is running inside a process with a lot of other things. So this chunk of memory is going to be next to the JavaScript runtime. It's going to be next to the document object model. So anytime you try to go out of this chunk, there's going to be checks that say, oh, wait, you can't do that. That isn't safe. So that is how security is maintained, is that whenever you're doing memory accesses, you only can access memory you're allowed to access. Another very important part of WebAssembly is foreign function invocation. So it isn't just its own thing. It's designed to integrate with JavaScript. So JavaScript can call into WebAssembly, and WebAssembly can call back out to JavaScript. And this means that you can build hybrid applications. Is you could, for example, build your front end or your UI in the DOM, and then delegate to WebAssembly to do some heavy lifting, like video decoding or game logic, or whatever you want. So if you've done any Android development, it's sort of along the same lines, is that you have to define what the interface is between the two languages. That's the top of the slide. It's just declaring two functions as the entry points and exit points. And then from that point, your two different languages can interoperate with each other. Now, here's where some of the evil genius comes into play, is because the web is a multi-party platform, everyone's invested, everyone's standardizing, everyone has their own implementation. Doing something new is difficult. It takes time. So how do you get people to adopt a technology when there's 1, 2, 3, maybe all the browsers don't support it natively yet? So the first version of WebAssembly is going to be designed to be translatable to JavaScript. Semantically speaking, you can just take this WebAssembly binary, spit out a JavaScript file, and run it directly in the browser. This means that browsers who don't implement can run it, but it'll just be slower. So if you have a native implementation, you can take in the binary file directly, it'll load faster, and it will run faster. This is roughly what it looks like. You start out with a C function. This just does 2 loads from memory, adds it together, and returns it. And then in the WebAssembly version, hand waving, this is binary, it has an operation tree, which essentially is the same thing, just explicitly naming what everything is. And then the JavaScript version, this is WASM.js, if you're familiar with that, is the first 2 lines are just saying, well, the inputs are integers, the 2 arguments are integers. And you see the or 0. Logically, that does nothing. But as a quirk of JavaScript, that actually turns what was a floating point number into a 32-bit integer, because you can't do Boolean operations on floating point numbers. And whenever you have a memory operation, instead it says there's this giant array. It's an array buffer. And we're going to treat it like the heap that we see elsewhere. Another thing to note is that in the WebAssembly version, there are no pointers. So what was used to be a pointer gets turned into a 32-bit integer. And it's the same as there's other data types like 8-bit integers, which aren't represented directly. They're just emulated on top of this. So it's designed to be minimal in the sense there's certain things which you'd think would be part of the platform but don't need to be. And it's designed sort of like a CPU, is that you just have bits that you're shuffling and computing on. So a lot of talking. Let's see it in action. So before I get too far into this, I have to say that all the numbers I am going to quote are actually completely unfair. And I am being unfair for a reason, sort of to illustrate the point. So this is all early work. This is a patched version of Chrome. It isn't in Chrome yet. This right here is a ray trace sphere, and it's running entirely in JavaScript. And it's running entirely on the CPU, no GPU involved, which in modern terms is kind of silly, but at least it shows what the CPU can do. Up in the right-hand corner, running about 30, 32 frames a second. And the program here is just a textual version of the binary format I whipped up so we could do some prototypes with. It's not the official syntax or anything along those lines. It's on my GitHub account. If you're interested, there will be a link later on. So it's about 30 frames a second. And now the question is, what happens when I click this box and I go into the native version of the backend? And we'll see that suddenly it's in like 80, 90 frames a second range. Now note that I said this is unfair. If I could claim a 2x performance advantage over JavaScript, there is the sales point there. But the truth of the matter is actually a little more subtle. So this example uses 32-bit floating point math, whereas naturally JavaScript works in terms of 64-bit floating point math. So when you have a number, for example, that's a 64-bit quantity, goes to the FPU. And when you have less bits for the floating point numbers, you can do them faster because you need less precision. It takes less clocks to pump them through. Now, JavaScript could do 32-bit floating point math fast. There's ways you can hint it. There's a JavaScript function called math.fround. And so every time you do a floating point function, you can immediately do math.fround after it, and then the JavaScript engine can say, well, because you're dropping those bits, I don't need to compute them in the first place. So if it was really smart, and some JavaScript engines are this smart, it could look at a sequence of math operations with fround and say, I will just generate the most optimal code possible for it. But as it turns out, this optimization has not been implemented yet in this particular JavaScript engine. And this is an issue of triage, as there's just more important things to do at the time. So in theory, JavaScript could run just this fast. It could run 85 frames a second. But the fact is that it doesn't. And it doesn't because of complexity and time. So the real win for WebAssembly is that it's simpler. It's simpler and easier to get the performance, and it takes less effort to get to the point where you have full performance. But I have full faith that JavaScript could do this if you throw enough engineers and enough money at it. Another interesting thing, I can't get this to reliably reproduce, but I'll try anyways, is we'll flip back to JavaScript. So when I did that, it just regenerated a new JavaScript program, compiled it, and started running it. So it's entirely different code. And then I flip back to the native code, same performance, flip back to JavaScript. There we go. So now you'll see that I'm down to 24 frames a second, whereas previously I was at 32 frames a second. Now, I haven't bothered investigating exactly why this is, but this is the sort of stuff you get all the time. Is I was doing something weird. Is I was just throwing more and more JavaScript at it, and at some point the JavaScript engine was like, okay, whatever, I've reached some threshold, and I'm not going to try as hard anymore. And now it's running slower. And this is what I started talking about as predictable performance. On the road to this, I did things like prototypes with shared memory, where I was trying to do fluid simulation and other parallel computation in JavaScript. And actually, I ran into all sorts of weird bugs that took a lot of time to understand why was it running slower. Like some of them involved invisible fields that were added to the objects to give them a hash ID because I was sending it to another process and it needed the hash ID to know if there were cycles in the object graph. So it was entirely invisible, entirely part of the underlying implementation. So that in a nutshell is WebAssembly. I have an uncle who's a salesman, and one of his quotes is, "Anyone can sell the future." So the question is, when is this actually going to be available? Now, all of these numbers are very, very tentative and possibly a little optimistic. They were sort of at the threshold where I said, what about 2016? And no one laughed out loud. But things are still under development. These are not a promise. So despite previously I was saying shared memory multi-threading is the most important thing to make native code on the web work, version 1 isn't going to have it. So version 1 is going to be more a canonicalization of what would happen if you translated it to JavaScript. Is you have a single thread, you have an event loop. But what you get is you get it to load faster and run faster and have more reliable performance. Then as soon as possible after that, we're going to add shared memory multi-threading. And why not make that part of version 1? And the answer is that threading is complicated as a user, but it's even more complicated as someone trying to specify how it works. So this is one of these like quagmires where you send soldiers in and they never leave alive. Is everyone who has tried to spec threads in shared memory has had a tough time of it. Now we can learn from everything that they did, and we definitely are, seeing what the C++ Standards Committee does. But we are being very cautious and not saying that we're going to block the release on this. And that's why the most important feature in my mind is actually not going to be part of the initial version. And then from there on out, there's all sorts of interesting things to add. One of the big ones for me is going to be dynamic linking. Is right now when you have a WebAssembly binary, it's just going to be one binary. So the question is, how do you share functionality between apps? How do you potentially update part of your app but not all of it at once, so you can have a partial download. And dynamic linking is a technique from native code, which if you use to JavaScript is like, what? It doesn't do that all the time, is where you just have multiple files that get loaded and turned into a single program. So that is all the prepared content, and let's do questions. We can get as technical as you want. I was just trying to spare you. I'd love to talk about it, but we'll see what people want to ask.
What is the expected performance compared to a native app?
We're going to try to get as close as possible. And for example, when you're translating to JavaScript, just like compiling native code to JavaScript, you can sometimes get like within, it varies on the app. You can like get within 2% in like the best cases, where I think you're pure numeric. So if it can look at the program and says, oh, this is a bunch of math, it can just generate the math and run directly on the CPU. But then when you start doing something with memory accesses, it has to validate all of those memory accesses and make sure they're in the right bounds, so there's more friction. Or if you have a call stack, at least with the translate to JavaScript, but WASM will be less of an overhead. Like the call stack also has overhead. So it's very mixed. Is translate to JavaScript I've seen on fast JavaScript implementations be pretty much neck and neck with native code, or sometimes be like 20, 30% slower. On bad JavaScript, well, I shouldn't say bad, but on JavaScript implementations that weren't tuned for this workload, is you can sometimes be like a factor of 10 slower. Native client, the experience was we told people around 10, 20%, and your expectations would be reasonable. And in some ways, this is the cost of portability. Like one thing I didn't get into is like bit shifting. Is how does that work when your number is too big? So you have like a 32-bit integer and you want to shift it by 33 bits. As it turns out, different hardware does this differently. And if you want something truly portable, then you have to sort of tighten that down and say, well, when you're out of range, it does exactly this. And then that adds cost to every bit shifting operation. So security is going to cost you, and portability in the sense that your program functions the same everywhere is going to cost you, but not cost you that much, especially when you consider you're getting threads and simmed out of the deal eventually, as you'll make up for it. Yes. So the question was, are there any touching points, was the phrase used, between WebAssembly and GWT? Is GWT still of interest to Google? So for those of you who don't know, I believe that GWT is a technology which transpiles Java into JavaScript, and I believe it's used for applications such as Gmail. I'm not Gmail. AdWords. Okay. Yes. And I cannot speak for is this of interest to Google. I'm just sitting on the web platform part. I'm trying to make this work. So there's people I cannot speak for. From our vision, eventually we would want to support this case. So if you're cross-compiling Java, it's a little more complicated because Java is a memory-safe language. And especially in the first version, is WebAssembly is not designed to have efficient support for garbage collection. You could do it, but it's not going to be as efficient as, saying, mapping onto JavaScript objects and relying on the JavaScript garbage collector itself. So eventually, version 2, we're going to think about memory-safe languages. But version 2, as far as I'm concerned, does not exist. Right now we're only focusing on the you got a bucket of bytes type languages and things that are implemented directly thereof, like Python. So, okay, one more from the audience. The question is TypeScript. It has types. Could WebAssembly be useful in that case? I personally would not use it. So there's an interesting point right here where the binary format has all sorts of types. And it would be nice to be able to say, hey, I have something that's JavaScript, but it has types. But that's going to be different than saying I have a big chunk of memory that I manually manage. So, TypeScript is sort of in between. And, version 2, where there's a memory-safe language, that might be worthwhile. But, a lot of these things that are transpiled to JavaScript were designed with JavaScript in mind. They have exactly the same concurrency model. They have shared memory, et cetera, et cetera. So I think they're always going to be best on top of JavaScript. So, okay, do we have any more questions on the app? Okay, no more. So there's someone raising a hand in the back.
Hi. Sorry. The other browser vendors, how in on the WASM game are they? Is it going to be a real standard, or are we going to end up with everybody doing their own different implementation of it, and it'll be the same mess as JavaScript and the DOM and everything else in the browser?
So one of these tricky lines to walk is I cannot speak for other browser vendors. However, this link at the bottom of the page, github.com/WebAssembly, is that sort of being used as a staging area for people to discuss things, to write things down. And you can go there and see for yourself who's participating. I think that if anything, we're coordinating a little too much, as we're planning too many things out. I personally want to see more prototyping, But in terms of lack of coordination, I can say that that's not a problem at this point. So the question is, who do I see as the target audience? I'm repeating this because it's being recorded, and I'm not sure you're being recorded. I think everyone heard him. This is a rather tough question. I mean, in the beginning, like all the game engine developers who are trying to target multiple platforms, these are very dedicated people, very technically skilled people. And there's always going to be those people who say, I can use this technology no matter what. But when we think about the web today, there's a lot of long tail. Pretty much anyone can get involved in the web. It's fairly easy to learn JavaScript. It's fairly easy to start writing applications. And when you're looking at something like native code, you're losing some of the features that make it a little easier to onboard, is you have to have a compiler in the loop. And I think over time, things like grunt, could be adapted to like rerun the compiler and regenerate your binary. But yeah, so I have native developers in the audience. I have front-end developers. Sometimes when we're talking about shared memory concurrency on the web, some of the JavaScript people get a little concerned and say, well, we don't see any need for this on the platform. So it's one of these, until it's actually there, it's hard to understand how the environment's going to evolve. And I think that one of the things that personally distresses me is how different the web platform is than the other platforms. So I think right now they're very separate ecosystems. And it's a little hard to see what's going to happen when they start merging. But when you're asking things like codecs, is like as a web developer, you could use a native library or it looks just like importing JavaScript, but it provides some high performance video encoding functionality or video decoding functionality, and it's just running in the browser. So you may not write it yourself, but you can still use it. Okay, so he's a native developer. He's using OpenAL and libvorbis. So libvorbis is pretty simple because that's just a codec. It's just computation. So you compile it, and it magically works, and it's magically high performance. No problem there. OpenAL is a little more complicated because that interacts with the system. It's an audio library. So you're saying, hey, I want to play this sound. Well, how does it get there? So one thing I waved my hands over and didn't go too deep into is that for version 1, you don't have any APIs. You just call out to JavaScript. So for future versions, we want to have web APIs directly bound to WebAssembly. But fundamentally, they're going to be different APIs. So it's going to be the same issue whether you have them directly or going to JavaScript, is you're going to have to write some sort of compatibility library on top of it. So someone somewhere is going to write a library that says, oh, here's the OpenAL interface. Here's how I implement it in terms of the web APIs for doing audio. And there's probably going to, like for OpenAL, because it's 3D, because the web currently doesn't have 3D, there's going to have to be some emulation of all the spatialization stuff on top of that. So ultimately, you compile your code, and you thunk into the web APIs, like OpenGL into WebGL. That's going to be a fairly simple one. Does that answer your question sufficiently? Okay. Anyone else? Okay, thank you for coming.